So the next speaker is Sadra Jazayeri. He will talk about cosmological correlators from flat space, Feynman graphs. So please go ahead.
Thanks a lot for the invitation and for the conference. So I'm going to talk about the work in collaboration with Sebastian Cespedes, and it is related to a couple of papers that I appeared in the past couple of years. But so I became aware yesterday by Kostas that there's going to be a talk related to this topic, so please keep an eye for that. So this is the list of things that I want to go through. Basically, I will tell you a theorem about cosmological correlators and a specific limit, which I love a massive flat space limit. And then I will tell you some application for phenomenology, for computing primordial Lagrangianity, and then I will leave you with some speculations. So I come from a cosmology community, so I feel obliged to put some pictures, but fortunately this Paul and the rest of the speakers, they the ground. So yeah, we just love inflation because it's a remarkable phenomenon that you look at the most infrared modes in the sky and then you can say something about the ultraviolet. I think that's the takeaway message for BBC. So the way that we learn about new physics in a scattering amplitude is very different from how we learn about new physics in cosmology. In cosmology, we just measure so we don't have control over the in and the in state. So the in state basically we assume that we start from a vacuum, and then all we can do is to let the universe to expand to infinity, and then start measuring the correlation functions of density perturbation. So that is how, and then the observables are also different. So you look at, for example, some Lagrangianity shapes in the sky, so on and so forth, to learn about new physics during inflation. So the talk is going to be about this loop of concepts, if you want. So over the past few decades, theorists have been writing down Lagrangians, primarily weakly coupled Lagrangians, to compute observables on the cosmology side. Usually this is a hard computation because Q with T in curved space to get analytical solutions is not easy. So the other way around to amplitudes is relatively easier, although some people might disagree, but at least if you are working with the scalars, it's relatively easier, but even for the scalars in cosmology, if you have massive fields and so on, it's very difficult. So it would be natural to ask, like, can you make a shortcut between amplitude and correlators? So there is a one-way pathway that we know something about. So that is about the singularity of the cosmological correlators, as Paul outlined in this morning, that in certain singularities are actually related on their residue to the scattering amplitude. But unfortunately, a scattering amplitude that you pick up by looking at the singularities are high energy scattering amplitudes. So if you have massive fields in the internal lines of the amplitude, they will just go to zero because you pick up the high energy field. And that's not very good. And the other way around, from amplitude going to correlators usually doesn't work because this is only the leading order singularity, and usually there are sub-leading order singularities, so it doesn't work. So in this talk, I try to address a similar loop, but so in this case, you see I replaced amplitude with some flat space of shell graphs. So let's say, can I go from flat space of shell graphs to some sort of cosmological correlators, which I love here, of-shell cosmological correlators, which I will explain. And I will try to convince you that there are certain correlators that you can read off simply if you know the answer in flat space. So, okay, so just to summarize again about the singularity. So if you assume that you have a complicated graph, in perturbation theory, there is a globe with various vertices, exchanges, loops, and so on, but it contributes to the 4-point function, let's say. And it is characterized by momentum. I should emphasize that momentum is very important. In this talk, also I should apologize that I'm removing the references, thanks to Kostas and Paul's and others' work. We know that momentum is not something that's just for the convenience of the cosmologists. There are some structures that you can only see if you look at the momentum space. So these are vectors. So these characterize the kinematics on the boundary. And then so this 4-point function develops a singularity if you do an analytical continuation in the sum of the size of the special momentum. So if you send this to 0, and that is only possible by considering either complex momentum or just simply analytically continuing to negative variables of the size of the momentum, the size of the special momentum, then you pick up a singularity and the residue is related to scattering amplitude. But as I said, the scattering amplitude that you pick up has 0 masses because, so basically what sending kt to 0 does for you is that in your time integrals, the singularity just comes from the UV, where all the masses are irrelevant. And so you get an in-out object, but it doesn't have any mass. So it would be interesting to see whether it is possible to start from the massive amplitude. So let's say you have a massive exchange, so you can just compute it in 2 lines. Whether you can relate this somehow to the massive exchange, for example, 4-point function. This is at 3 level, and then for any other stuff.
Sorry, you're not wearing a mic.
Oh, okay.
Press the button to switch it on.
Yes, so. Sorry. So I will not. So I won't give you an answer for this specific question, but a closer question to this will be that: can I relate the off-shell correlators, which I define here, to a certain objects in flat space, which will be some off-shell Feynman graphs in flat space? And the answer is yes. So the way that I define the off-shell correlators is simply that you just, so first of all, I'm talking about in-in. So in your in-in computation, you have bulk to boundary propagators. So you have phi plus and phi minuses. These are the positive and negative frequency of your field, let's say. And they have, so they depend on the momentum of the external leg. So now the momentum of the external leg is given by the special vector, but let's substitute this with some independent variable. You can call it energy. The fictitious energy. It's a bit of a bad terminology, but let's run with it. And then, so in perturbation theory, this defines a function, an extended function that depends on these external energies, and it's an off-shell object because omega 1 is not omega 1 squared is not k1, not k2. So this is simply a natural definition of off-shell correlator. So now let's define another object, the massive flat space limit. So the idea is that you want to take the flat space limit. So if you send all the energy, or previously I said the sum of the energies, but I want to here send all the energies to 0, which is a particular limit of sending all the sum of the energies to 0. You pick up the UV part of the time integrals, and that is not very good if you want to keep the information of mass, because all the masses becomes irrelevant. So the idea is that to send also the mass to infinity. So you send omega to 0 and mass to infinity. But in order to not get something that is just obviously singular or 0 or infinite, you also want to keep the product fixed. So if you do that, so first of all, I should tell you that what is the motivation for doing this. First of all, this is an off-shell object. So omega is not k. So what you're computing is not an observable. But it becomes an observable if you do not look at the de Sitter invariant correlators. So I'm not looking at the correlators of massless fields, but let's say I'm looking at the correlators of some sort of massless field in de Sitter, which Brecht boosts, and it has a speed of sound, meaning that the dispersion relation has some additional parameter, the speed of sound. And then this massive flat space limit simply means that I'm sending CS to 0 and mass to infinity in such a way that this parameter is fixed. So in this case, you are actually computing something that is related to observable. I'll tell you in a moment that how this is related to the effective field theory for inflation, in which the fluctuations have a speed of sound. So this is the massive flat space limit. And then can you tell me how much time I have, because I'm red shifting in my head.
I mean, if you want to take questions during your talk, that's, so we can go for like 15 minutes.
Okay, 15 minutes. Great. So the theorem now is the following, that in the massive flat space limit, the correlator simplifies. So on the left-hand side, you have a generic multiple exchange diagram, multiple loops with various vertices. But if you take the massive flat space limit, this just collapses into a single contact term. And the contact term is special because the vertex factor that appears in this contact term does not come from a local Lagrangian. Instead, it is given by an amputated Feynman graph in flat space. So this is the cartoon of how this limit looks like. But more precisely, this is exactly the relation. So F, by F I mean the correlator, so it depends on the momentum, it depends on these energies, and it depends on the mass. So in this limit, it is given on the right-hand side by an object that only involves one vertex, so there's only one time appearing in this. And then the vertex factor is something that depends on the external momentum, but in a specific way. So the four momentum that appears in the argument of this flat space object, they depend on time. So they have zero energy. After all, I'm taking all the energies, external energies to zero. So it's a completely spatial four vector. But the spatial part of the momentum redshifts with the scale factor. So that is a kind of a instantaneous scattering amplitude that you can define at each moment of time during the theta. And then you have to integrate over it and multiply it by the bulk to boundary propagator to get this correlate. So who tells you that this relation is correct? So first of all, we have checked this numerically for tree level. It's very hard to check these things, even for, let's say, even for the exchange diagram that I was showing. Even for this, because the full bootstrap answer for this involves these hypergeometric functions with indices that depend on mass, and then taking the large mass regime of hypergeometric function is actually an open area in in mathematics today. So it's not easy. So the best I could do was to just numerically check that this is true. However, there is a rationale behind the yes.
But the hypergeometric function was actually just an integral of some times, right? Like
yes.
Time integrals of something.
Yes, yeah. Sure. You can directly check it at the level of the time integral, so to speak. So you can check it, but it would be nice also to just look at the final answer and take the massive flat space limit and see that whether it pops out the amplitude. So I'm saying that I have a numerical check of that. But also at one loop, we checked it using so if you know it at tree level, basically using the spectral decomposition of one loop graph, you can also show that it is valid for one loop. But in general, the rationale comes from an effective field theory point of view. Basically, it tells you that you are taking the massive flat space limit, so where the Compton wavelength of the mass of the massive object is much smaller than the Hubble. Therefore, you are interested in the correlators of the massless field, the light field. So you can integrate out the massive field, but the path integral doesn't have to be a Schwinger-Keldysh path integral, because this field doesn't know that there is a horizon. So it is as if you are in flat space, and then you get an effective action. But the effective action that you get is generally non-local in the field, and the reason is precisely because I'm sending these external energies to zero. When you send the external energies to zero, it means that you are sending the conformal times at each vertex to minus infinity, and therefore the kinetic energy, k times eta, is big. It's comparable to the mass. So you cannot expand in k over mass. So the object that you get is non-local in space. So it's a non-trivial thing. So it's not obvious how to do it, but so at tree level and one loop. It's possible to check it. So the application. So the application comes from computing the signatures of massive fields during inflation. So now I want to look at inflation not only as a massless scalar in the theta, because that only covers a minimal space in the space of inflationary models. The more general framework to describe a single field inflation is the effective field theory for inflation, which is the effective field theory basically for the phonons during inflation. These are the phonons that tell you how the theta isometries are broken during inflation, and the breaking of time translation symmetry is non-linearly realized by this Goldstone boson. So basically these at the end give you the scalar fluctuations during inflation, but the Lagrangian also allow for a speed of sound. And basically this speed of sound is very important because this is one of the main targets of future observational targets for primordial non-Gaussianity. Because if there is some non-Gaussianity, the first this would be the first hint towards having a non-trivial speed of sound. Because if the speed of sound is 1, then you can see that the FNL actually goes to 0. It is a slow roll suppressed. So if you have FNL of order 1, this is an indication of breaking boost during inflation. So the speed of sound is important, and it could be still by the current Planck data, it could still be taken as a small variable. So it would be it could be taken as a parameter that is much smaller than 1. And finally, the mode function that I was specifying. So this is the massless mode function of this field in the theta. And if you take eta to minus infinity, if you go in the UV, you see that you can basically describe this as a plane wave with a dispersion relation that omega equals Cs times k. And that brings me back to the questions, to the motivation in the beginning, that now I can use this massive flat space limit to compute diagrams like this. So imagine that you have a massive particle and that it is coupled to this phonon field, and then you want to, for example, look at the one loop effect of fermions, so species that do not even couple at theory level. And it's a very hard computation, so I'm not aware of explicit bootstrap results even for this simple diagram. But in this massive flat space limit, as I told you, it becomes a very simple computation. Basically, all you have to do is imagine that you have a bubble diagram that is very complicated, but you have computed it already in flat space, let's say. So it's something like a vacuum polarization. This is pi as a function of p squared, the ingoing momentum, and you have computed it, let's say. So if you have two vertices connected by a single line, it's a tree level, you just have 1 over p squared plus m squared. If it's a one loop, then you have a branch cut, so it's a more complicated object. But nevertheless, it's very simple to compute in the massive flat space limit, let's say the 4-point function is in S channel. So you can forget about how many vertices you have. You only have one vertex, and the vertex factor is given by this vacuum polarization. And computing the time integral is also easy. We borrowed some ideas from Mellin transformation, so you can do the Mellin transformation of the off-shelf Feynman graph, and that hugely simplifies the time integrals, and then you can rotate the contour and write appropriate expressions for the 4-point functions. For example, already at tree level, you get a nice expression, so the 4-point function becomes a logarithm multiplied by some polynomial. And at one loop, it's the same structure appears, although you get the square of the log, so on and so forth. And from this 4-point function, you can read off, for example, the shape of non-Gaussianity. So in this particular tree level signal, we computed the shape, and we discovered actually a smoking gun imprint of this particle. Remember that we are computing certain massive, the signatures of certain massive fields that move at the speed of light, and the external legs, your inflaton perturbations, are moving very slow. So these are supersonic particles during inflation, and you are computing their signature. And their signature actually give you a bump in the 3-point function, and this bump was actually looked for in the recent data analysis of Bose Galaxy and CMB data. And you won't be surprised that there were no evidence for this because it's the data is still galaxies are hard. So I leave you with some speculations. So I told you now the relation between off-shell correlators and off-shell Feynman graphs in flat space. So the natural question is that, can you tell me a relation between on-shell correlators and scattering amplitudes? So the reason that I tried to do this, but it seems that it is more complicated. Notice that when I was discussing these off-shell correlators, I was sending mass to infinity. And in the theta, so the reason that I ended up getting the Feynman propagators in flat space and not the other propagators like plus and minus propagators in flat space is that the particle production in the large mass regime becomes small when you take the large mass regime. However, when you take this specific flat space limit, that is not very obvious, because although you have contributions that go like e to the minus pi m over h, like the Boltzmann factor, you have branch cuts. And when you send some of the external energies to minus the external energies, there are some branch cuts that could compensate these Boltzmann suppressions, and that could actually complicate or make the situation more interesting. So I don't know, but we should. I think that this is interesting to explore further. So some on-shell massive flat space limit, and then once we have this, so this is a bit far-fetched, but so the idea is that if you know something about the amplitude limit of correlators, can I do some dispersion relation as people do in scattering amplitude in the KT space? So let's say. So what's the correlator or effective filter? If you have an effective filter, you have like a Lagrangian in terms of phi with higher order derivatives. The correlator, if you compute the correlators, you see that they appear in increasing powers of 1 over KT. Because if you add more derivatives, you pick up higher and higher order poles. So this suggests that so these EFT correlators are defined in this KT space at the large arc. So this is like an expansion when KT goes to infinity. So this massive flat space limit tells you something about the behavior of the correlator near the origin. So now, so this looks like a relationship between IR and UV. So it's suggested that maybe we know a lot about the positivity of the amplitude. So can I write some dispersion relation to like relate these coefficients to some properties, some positivity properties of the amplitude near the origin or not? So I think that could be another application of this correlator amplitude relation. Thanks for your attention.
So we have maybe time for a couple of questions. Where is the mic? Because it was the one I gave him.
What is the other one?
Oh, you're still wearing one.
I'm still wearing it.
Maybe just a comment for this last part.
Yes.
I think what is straightforward is if you start with massive amplitudes in the sitter, you can take a limit to recover massive amplitudes in flat space.
Yes.
So that would mean take h to infinity while you keep fixed the mass, so you don't take m to infinity.
Yes.
But I think, as I understood it from your talk, is that you're more interested
In the other
way around.
Yes,
in a
yes.
sense, how do you go from massive amplitude to
Yes.
flat space? Okay, that of course it's more non-trivial.
Yes, yes. Yeah, I think that we will hear about this point of view on Friday by Rafael.
Any other question?
So if I may ask one, I mean, do you have an intuition for how you would do this even for massless? Like if I gave you a massless scattering amplitude?
Oh no, so that is more that is far more complicated. The reason is that I don't know how to take the flat space limits in a way that like particle production becomes unimportant. Because amplitudes do not know about particle production, right? I mean, you just conserve the energy. So, but in the sitter is different. I mean, no matter how small the energy of your external legs are, you produce the particles just because of the expansion of the universe. But if you have massless particles, you always produce them because of the expansion. So if you don't have any other parameter like mass that you can play with, okay, so you send mass to infinity, you don't worry about the expansion of the universe, then I don't know how to do it. Except for this usual total energy singularity that picks up the amplitude. That also holds for massless fields.
Okay.
Yeah, so I don't know how to do it for light fields, let's say.
Okay.
Cool.
Very good. So if there is no other questions, thanks again.